Well, good day. We're talking today about what is this dx stuff on integrals. It's really pretty easy. We're going to make it clear for you. So stay tuned. I don't think you have to write one thing down. This video will make more sense to you if you just absorb and take it all in. So we'll take a look at the notation of both the integral and the integrand and the dx. In the end, you'll realize, oh, I see what that dog's all about. So let's take a look immediately. We're going to look at the integral from 1 to 5 of the function x squared plus 1 dx. For that integral, we want to answer the question, what is this dx stuff? I don't get it. So anyway, we're making a table of values here for the function x squared plus 1. Furthermore, we're going to graph this function. We've got a nice viewing window. X values 1 to 5 as the limits of integration are 1 to 5. And this thing will creep up to 26. So the y-axis is going by 5. And we can accommodate that final order pair. Here are the points. And of course the parabola and the interval endpoints as vertical lines there as we are integrating from 1 to 5. So we're going to break this down and try to understand a little bit about that dx. We're going to have a progression and build up to it. Stay tuned. So with this graph, it's the identical graph that we've just seen. And this table, it's the identical table that we have just seen. The first part of this progression, we're going to challenge you to calculate the left-hand sum with 2 intervals. Well, if I'm going to use the left-hand sum with 2 intervals, the rectangle is going to have a base of 2. So I go up to the curve and directly right, up to the curve and directly right. Those are my 2 rectangles that I need to find the area for. I steal these 2 ordered pairs from my table. So I see the height of rectangle 1 is 2, the height of rectangle 2 is 10. Each of those rectangles has a base of 2. So I realize the area of a rectangle is base times height. It's going to help you if you think about the area of a rectangle as being height times base. You know, 2 times 5 is the same as 5 times 2, so I can switch the order here. It's just going to align better with our integral notation in the end. So I see here the heights of my 2 rectangles are 2 and 10, while the base of each rectangle has a length of 2. Do the math and I get 24 as a left-hand sum with 2 intervals. Progression number 2. We've got the same graph. We've got the same table. This time we are going to do a left-hand sum with 4 intervals. These are the 4 ordered pairs we're going to use so that you can then see the height of each of these 4 rectangles. Up to the curve, directly right, up to the curve, directly right, up to the curve, directly right, up to the curve, directly right. Gives me these 4 rectangles. Each rectangle has a base length of 1 and height determined by the outputs from the table. So again, if I am to figure out this left-hand sum, I got to add up the area of these 4 rectangles. Well, the heights are 2, 5, 10, and 17. And the base of each of these rectangles is a simple 1. So I do the math and get 34 times 1, which is 34. Third progression. We're getting there. So again, you're going to see both the graphed parabola and its table. This time, as you may predict, we are going to calculate a left-hand sum with 8 sub-intervals. Here are the 8 rectangles determined by these 8 outputs. I see this time that each rectangle has a base length of 0.5. Again, I'm thinking of the area as height times base. There are the heights of all 8 rectangles times the base length of 0.5. This gives us a sum of 79 times 0.5, a left-hand sum of 8 intervals equal to 39.5. We're not supposed to learn how to do left-hand sums in this video. This is all about finding what is this. We got to explain what dx is. Yeah, this next screen will show you the light. Take a look. Same exact graph, same exact table of values. This time, I want to calculate a left-hand sum in our last progression. And with this left-hand sum, I want to use not 2 rectangles, not 4 rectangles, not 8 rectangles, not 16 or 32 or 64 or 100 or 1,000 or 10,000. The truth is, I want to use an infinite number of rectangles. An infinite number of rectangles. So if I'm going to put an infinite number of rectangles in there, these rectangles are going to be pretty scrawny. Their base width will not be that long. You can see an infinite number of rectangles. Well, I've cheated on this. That's really not an infinite number of rectangles. It gives you a nice picture, and you can see that if there were an infinite number of rectangles in there, the entire area would be completely filled between the curve and the x-axis. You've seen that action on your calculator when you have evaluated integrals like this one from 1 to 5, and you integrate, and then the calculator from left to right fills in that area space between curve and x-axis, and it kicks out the area answer. So anyway, it's important that you see all of these rectangles. Let's take a look further. Again, thinking about the area of a rectangle, each rectangle as height times base. Well, every single rectangle I can determine the height. The height of every rectangle, no matter the x coordinate I put in, is going to be determined by the formula x squared plus 1. So the output for each height is simply the value of f of x, like f at 1 or f at 1.7 or f at 1.8675309. I can figure out an exact output for all of those by putting those x values into the function. In doing so, I will get the height of every rectangle. How about the base? The base of each of these rectangles. Well, what is the length of the base of each rectangle if I have an infinite number of rectangles within that region? It's not 0. That width might be approaching 0. It is infinitesimally small, but not 0. We represent this with a dx. So f of x dx is really just a formula for finding the area of a single rectangle. And the integration is telling us we're going to do that for every single rectangle between 1 and 5. Further addition here, see if we can make things clearer. What is f of x? F of x is the height or output of the function. The height of every single rectangle, which I can determine from the output of the function. D of x, then, I need to think of that as that small difference in x. dx, difference in x. That very small difference in x, what you described as being infinitesimally small, but not zero. Boy, if it was equal to zero, our whole scheme would be absolutely crushed. Small difference in x, infinitesimally small for an infinite number of rectangles. So hopefully that gives you a picture of why that dx is necessary. I mean, your teachers always said, don't you dare write an integral without tagging it with a dx. Well, what's the dx for? What's the dx for? What's the dx for? What is the dx for? What's the dx for? Well, what that dx for? Well, now hopefully you see why that dx is necessary. So, hopefully you've had a lightning bolt understanding of this dx scenario. My advice to you, when you see the command integrate from 1 to 5, x squared plus 1 dx, think of it as, first of all, that integral symbol. That symbol looks like the letter S. Think of it as summing up the area of an infinite number of rectangles, positioned from, in this case, x equals 1 to x equals 5, each with area height times base. Height times base, which you now equate to f of x dx. I challenge you at this point to find the integral of from 1 to 5 of x squared plus 1 dx. Do it by hand using FTC1. Then confirm your answer on the calculator. And then try to think and understand it as what you have just found. The total sum of all the areas between 1 and 5 of these rectangles, each of which has a height of x squared plus 1 for every x value between 1 and 5. Hey, hope this helps. This explanation made a great deal of sense to me. The pictures make a lot of sense. I look online and see a lot of jibber jabber, long explanations that I don't understand, or one-liners that really don't do dx justice. Hope this makes things clear. I believe that it will, and you can pass this information along to someone else. We'll see you soon. Calculus Made Easy. Over and out.